Welcome to SysSketch. Today we're answering a question that trips up almost every networking beginner. What does subnetting actually do and why does it exist? Before subnetting, imagine every device on your network sharing the same broadcast domain. A /16 network gives you 65,534 host addresses all on the same wire. Every ARP request, every DHCP discover, every SDP packet floods every single one of those hosts simultaneously. Traffic becomes noise. Security becomes guesswork. This is the problem subnetting solves. At the core, every IP4 address is exactly 32 bits, 4 octets. Take 192.168.10.5. In binary, that's 4 groups of 8 bits each. The subnet mask decides which of those 32 bits belong to the network and which belong to the host. Network bits are shared by every device on the same subnet. Host bits are unique per device. Mechanism is a bitwise AND operation. Your router takes the IP address and ANDs it bit by bit with the subnet mask. Wherever the mask has a 1, the network bit is kept. Wherever the mask has a 0, the bit is zeroed out. What remains is the network address. For 192.168.10.5 with a /24 mask, the result is 192.168.10.0. That's the network address for every host in this subnet. So what does each half of the address actually control? The network bits identify which subnet a device belongs to. It must match for 2 devices to communicate directly without going through a router. The host bits identify the specific device within that subnet. All zeros is the network address itself. All ones is the broadcast address. Everything in between is usable for hosts. More host bits means more devices per subnet. Fewer host bits means more subnets, fewer devices each. CIDR notation gives us a compact shorthand. 192.168.10.0/24 means 24 bits are locked as the network identifier. That leaves 8 bits for hosts. 2 to the power of 8 minus 2 gives you 254 usable addresses. The slash number tells you everything: the mask, the host count, the subnet size, all in one figure. Practice subnetting lets you carve up address space precisely. Take 192.168.10.0/24. Borrow 2 bits from the host portion and you get 4/26 subnets, each with 62 usable hosts. Subnet 1 covers .0 to .63 your servers. Subnet 2 .64 to .127 your users. Subnet 3 printers. Subnet 4 IoT devices, each isolated from the others at layer 3. Why does any of this matter? 4 reasons. First, security isolation. Devices in different subnets can't reach each other without passing through a router or firewall. A compromised host cannot attack devices in another subnet. Second, broadcast containment. Broadcasts stay inside their subnet. Smaller broadcast domains mean less noise and faster effective throughput. Third, IP address efficiency. CIDR lets you allocate exactly the space you need. A /30 for a point-to-point link wastes just 2 addresses instead of 254. Fourth, routing efficiency. Routers forward on network prefix, not individual hosts. Route summarisation keeps routing tables compact even at internet scale. Keep this table close. /8 gives you 16 million hosts. /16 gives 65,000. /24 is your standard LAN, 254 hosts. /26 gives 62. /30 just 2 hosts, perfect for router-to-router links. Every prefix is a trade-off between the number of subnets and the number of hosts per subnet. The formula is always the same: 2 to the power of host bits minus 2. Let's put it all together. An IP address is 32 bits. The subnet mask performs a bitwise AND to split that address into a network identity and a host identity. The network address groups devices into a subnet. The broadcast address reaches all of them. CIDR notation encodes the mask as a prefix length. Routing tables match on prefix. VLSM lets you use different prefix lengths across the same network. And RFC 1918 ranges 10/8, 172.16/12, 192.168/16 stay private and are never routed on the public internet. That is subnetting, the atomic unit of every network on Earth. Thanks for watching SysSketch.